understand. What do you want? You're just a machine. You're just a machine.
Alrighty.
There we go. That should be a little clearer. All right. Yes, I will be happy to share the playlist on Piazza afterwards. All right. Uh, let's get into it. Um, so last class, we talked about relational algebra. And in particular, we introduced it as a framework for reasoning about queries. And as you recall, last class, the kind of goal was to be able to look at a bunch of problems. So over the course of the class, we're going to look at a bunch of problems and kind of figure out the design space for solutions to those problems, whether they be data structures or algorithms or kind of hybrids of algorithms. And once we look at the design space, we essentially want to find out all of the solutions that will produce the same answer, that are equivalent in some way, and we want to find the ones that are better. Um, Now, last class, we started looking at query processing. And in particular, we looked at, we started building up a framework that we could use to reason about what the design space of a solution to a query would look like. Um, it's a little abstract. So more precisely, we looked at relational algebra. And uh, the thought was essentially that we could use relational algebra to model how we go about solving or answering, how a database goes about answering a user's query. Now today, what we're going to focus on is we're kind of going to take another step towards using relational algebra to optimize query processing by looking at what it means for two queries to be equivalent, or two relational algebra expressions to be equivalent. And depending on how you want to look at this, essentially we're either going to kind of figure out whether two queries are the same and prove to ourselves that two queries are the same and that both of them are candidate solutions, candidate algorithms for solving the problem. Or if you want to look at it in a slightly different way, we're going to come up with a couple of techniques to start with one relational algebra expression and then start generating new relational algebra expressions that we can prove to ourselves are answering the same question. So what do I mean by that? Well, I have two queries and I want to be able to decide whether they're the same. Now, obviously, here are two queries. There is some sense in which these queries are different. They're different queries. So what we're interested in is trying to find out, well, what does it mean for the two queries to be equivalent? So to that end, let's set ourselves some ground rules for what it means for two queries to be the same. So first off, what we're interested in isn't the actual structure of the query. What we're interested in is, if I give you two queries, are those queries going to produce the same results if I run them on the same input? Um, and more importantly, this should hold for any input that I can produce. So given any input data that is valid for both of my two queries, I want to prove to myself that they're always going to produce the same output. Um, Now, a small aside, we'll talk about later in the semester, we'll talk about some more interesting cases where we know that the input data set has certain properties, and how we can take advantage of that to give ourselves even more equivalent queries. But at least for now, what we're interested in is, if I give you any data set that is a valid input to both queries, can I prove to myself that the output of those queries is going to be the same? Now, the final thing we have to keep in mind is whether we're talking about sets, bags, or lists, because two queries might produce the same bag as an output, but the list that they produce is going to be different. Or similarly, two queries might produce the same set as an output, but they will have different counts of the resulting tuples. So today we're going to focus specifically on bags because that's what most database engines use, and we'll kind of periodically glance back and see if any of these rules also apply to sets, and then we'll get to lists in a couple of weeks. And then the final note here is that we care about the content of the data, not necessarily the representation or the encoding. So in particular, where this comes up is that the order of the attributes doesn't really matter. So as long as we have the same set of attributes in our data set, as long as each of the attributes is represented, then we are happy. The order doesn't matter, although the count does. Okay, so to summarize, what we get from those ground rules, two queries, I'm going to call two queries equivalent, symbolized by that little hamburger there, if and only if we can guarantee that if I run one of the queries on a particular input, I will get the same bag of tuples as if I run the second query on exactly the same input, and that this holds for any possible valid input that I can feed the query. Do a little quick pause for questions. All right. Right. Okay, so over the course of this class, we're essentially going to talk about how we can prove these. The order of the attribute matters in the case of joins or cross product, or does it not? Yes, so that's exactly what I'm referring to here. The order of the attributes doesn't matter. So, well, I'll get to that in just a moment, but the order of the attributes doesn't matter. The only thing that matters is that all of the attributes are there. Good question, Manasa. Okay, right. So um, the idea here, so I've been calling it relational algebra, and that's maybe a little bit weird. You might be asking yourself, why is it called relational algebra and not the relational language or some sort of fancy thing like, I don't know, relation? Um, and the reason for that is that relational algebra is what's called an algebra. It's a mathematical model that we can use to kind of reorganize the expression. So think back to high school or even maybe middle school when you started learning about algebra, or actually maybe even earlier, where you started learning about variables and kind of your basic algebraic manipulations. So if I have, for example, a times, and then in parentheses, b plus c, if I have a times b plus c, like for different people learn this at different stages, but essentially you can always take that expression and rewrite it into a b plus a c. There's a property of addition and multiplication called distributivity, where you know that if you feed the same inputs, if you put the same A, B, and C into this query, you're going to get back the same exact output. If you feed the same inputs into both of those expressions, you will get the same outputs. So we're going to start off with a couple of these basic rules, and then we're going to, over the course of the class, essentially prove to ourselves that come up with a bunch of new rules, starting from these rules and a couple more that I'll introduce over the course of the class. I'm going to present these as just ground truth for you. I'm just going to tell you what they are, maybe give you a little intuition for why. If you want to learn more, I'm happy to talk to you during office hours or to go into more detail on Piazza. Okay, so our starting rules here. So the first thing is if you apply a filter, if you use a selection operator on a table, and that selection, the condition of that filter has an and in it, it's a conjunction, then it's essentially the same thing as applying uh, the two selections in sequence. So filtering all of the input for condition one, uh, sorry, for condition two, and then filtering all of the input for condition one is the same as filtering on both condition one and condition two. For projection, so projection is what we call idempotent. You can cut the input down to a specific set of attributes as many times as you like, but you're always going to end up with the same set of attributes. And in fact, you can always add more attributes as you go down the tree. The only thing that really matters is the set of attributes at the very end. So if I have a projection for a set of attributes A, that is going to be produce exactly the same result as if I apply the projection to then another projection that includes at least the attributes in A and then maybe some other attributes B, and that gets applied to the same input. Cross product. So very much like multiplication, cross product is both associative and commutative. In other words, you can change the order in which you evaluate things. And remember, because we don't actually care about the order in which the attributes appear, we can also flip the order in which the inputs appear in a cross product. And similarly, union is also associative and commutative. We can change the order of operations and we can flip the order of the inputs as we like, because it will always produce the same bag of outputs. We'll pause for questions here. Usually there's one or two people who there's usually quite a few people at this point who are either confused or need a little bit more information. Ah, you're all getting it. Okay. Well, oh, can I explain projection again? The projection rule. Okay, so look at it this way. Let's say we have a table. I'm going to call it R, and that table has three attributes: A, B, and C. And since we're using bags, the specific values here don't matter. So if I apply a projection, if I project this down to the attribute A, so project of R down to just A, what do we end up with here? We end up with 1, 4, 7, right? Now, let's say instead I did a projection of this down to just A, B. I end up with the attributes A, B, 1, 2, 4, 5, 7, 8. So I can go directly from my original R to projecting down to A, or I can first project down to AB and then project down to A again. So this is essentially equivalent to projection of A of projection of A B of R. And it doesn't, I'll get exactly the same bag of outputs. So hopefully that addresses your question, Karan. If not, I'm happy to go into more detail. Adesh asks, is there a case where you prefer union over cross product? I'm not sure I understand that question because union and cross product are very different. Are you maybe asking about join and union? Sorry, join and cross product? Well, if you're asking about join and cross product, we'll get to it in a little bit. If you're asking specific, okay, so we'll get to join and cross product in a little bit. Okay, so moving right along. Okay, so we have a bunch of rules that we've come up with here. Let's actually try to do something with them. So our rule here is we want to essentially show that these two expressions are the same. So let me copy them over, R cross S cross T. And we want to show that this is equivalent to, what did I say here, T cross S cross R. I usually like to do these interactively. Hopefully the stream latency is low enough today that we can pull that off. If not, we'll do one or two, and then I'll go through the others on the board. But let's see if we can do something interactive here. So R cross S cross T. Now, there's no rule that I've given you so far that shows that these two are equivalent. So, but at least in principle, we should be able to take some of the rules that I've shown you. For reference, we'll go back. We should be able to take some of these rules and apply them in sequence to come up with, to transform one of these into the other. So I've been yapping for a little while. Let's see if what can I do? What can I do here? What kind of rules are applicable in this situation? Associativity, great. So one thing I might want to do is throw some, apply the associativity rule to the left-hand side. So that basically gives us R cross S and then that cross T. So we know that those are equivalent. And commutativity. Okay, so I can apply then commutativity to the final result and get T cross R cross S. And what else? That's not quite the same as the output. Good job, Karan and Sukhya. Stream latency might be a little bit high for this. So we're not quite there yet. Remember, what we're trying to do is get to here. Again, commutativity. Yep, so T cross. Now if we apply it to the inside, we get T cross S cross R, which is exactly the same as what we originally asked. Fantastic, Adesh. All right, great. So we have that those two are equivalent. Great. Okay, so let's keep going. All right, so this one might be a little more tricky. So what we're trying to show here is that if we apply a filter on, which order did I have here? C1, and then we apply that to the output of a filter on C2 of R, then we want to know if this is the same as applying the second filter to the first filter of R. All right, so what options do we have here? decomposability. Okay, well, we apply decomposability in reverse, and we can combine these two, or I guess compose the two, C1 and C2 of R. So we know those are equivalent. Now what? Good job, Ben. So idempotence is only going to apply to projection. Then commutativity. Okay, interesting. So here I'm actually cheating you a little bit because I haven't actually given you the tools to solve this particular problem. But yes, exactly. So and is also a commutative operator. And you might have picked this up from middle, high, whatever, or pre-college school. So this is going to be exactly the same thing as C2 and C1 of R, because and is commutative. Okay, it's not. And let's wrap it up. Decomposability again. Fantastic. Great. So so this is now the same as C2 applied to select C1 applied to R. Great. Okay. Fantastic. So now those two are equal. Great. Where are we? All right. Latency isn't actually that bad, so let's do one or two more. So R join on some condition S, and then S join on the same condition R. Okay, what can we do here? This is also a little bit of a trick question, but I have, at least over the course of the last week and a half, given you the tools that you need to solve this. Commutativity, okay. That's actually an interesting question because I haven't given you a commutativity rule for join. I mean, if join were commutative, and maybe it is, but I haven't actually given you a rule for join. So um, decomposability. Okay, what do you mean by that, Kaushik? I think you're on the right track, by the way, but what do you mean by that? Converting to select, okay, Harsh, perfect. So as we said last week, what is a join? A join is just a selection sitting on top of a cross product. So we can always take this, and this is always going to be equivalent to selection of that condition of R cross S. And now once we have that, well, great. Okay, yes, exactly. Y'all are on the ball here. So once we have that, now we have the commutativity rule for cross product, and we're good. So selection of S cross R, and then we can always convert that back to a join. S join C of R. Now, I wanted to go through this exercise just to get you to recognize that essentially another rule in our toolbox is the fact that join and selection sitting on top of a cross product are essentially the same thing. So uh, that's important to recognize. We'll get back to that a little bit later in the class. But knowing that, join and knowing that, and one of the other rules that we're going to talk about in just a few moments, you can prove to yourself that join and that join is both an associative and a commutative operator. There we go. Okay, last one. So here I've got another condition. I've got a selection of R, B equals S, B, and S dot, what did I say, C, R dot A. R dot A is greater than 3 of R cross S. And we want to show that this is equivalent to selection of R dot A is greater than 3 of R join on B of S. Okay, so what do we do here? Decompose the right-hand side. Okay, so we can, yeah, let's start from the right-hand side here this time. So we're gonna turn that into R A is greater than 3. So the direction in which we do this doesn't really matter. Select of R dot B equals S dot B. And remember, B being there is essentially, this is, the B there is just a shorthand for this of R cross S. And once we have that, we can apply our earlier rule to combine the two. And then take advantage of the associativity of join. So R A greater than 3 and R B is equal to S B of R cross S. And then that's the same as R B equals S B. And then the same R A greater than 3 of R cross S. And great, we've shown that the two are the same. Great, okay. So there's a little bit of a warm up. Now let's talk about how the different operators interact with each other. So selection and projection fairly often, selection and projection can be commutated with each other. The order of operations, we can flip the order of operations, but only under certain circumstances. There's already a post on Piazza, so I know at least one person has noticed a case where this does not hold. What do I mean by compatible? Same schema. Um, you're essentially on the right track. So essentially C had better not use one of the attributes that the projection is projecting away. So for, yeah, exactly. Yeah, Ben and Soham, that you've nailed it right there, Soham. The if so the expression on the left-hand side might be valid. The expression on the right-hand side might not be valid if C uses one of the attributes that doesn't show up in A. So just to be clear, you can always go from right to left because you're, in that case, C is guaranteed. If C is correct, if C is valid, you're never going to make it invalid by adding more attributes, but there might be some situations where you can't go from left to right. Okay, so let's try it. Let's combine some of the rules here. So we've got all right. And yes, we are only so interesting. Interestingly enough, this still holds for both sets and bags. All of this, this particular rule and the projection idempotence rule hold for sets and bags. But today we're focusing on just bags. So assume we are working with bags here. So let's get from one to the other. Okay, idempotence on Soham, you were first, so let's go with the left-hand side. Um, so idempotence on the left-hand side, so projection of A. So this is the same as doing projection of A and projection of A union the columns of that show up in C. So we can always add a new projection. One more. And then, so we've got idempotence, and well, in the interest of time, this is where we apply this new rule that we just discovered. So we can always, since pretty much by definition here, the projection does include all of the columns that show up in the selection. This is guaranteed to be equivalent to projection of A, selection, and project A union the columns of C of R, 1, 2, 3. And now these two are, we've just proved to ourselves that those two are equivalent. Great, so let's keep going. Selection is we can take a selection and a cross product, and we can always push the selection down into the cross product. Again, assuming that the attributes work out. So in order to do this, we can always go from right to left, but in order to go from left to right, it had better be the case that the only conditions that are being used here are the ones where sorry, the only attributes that are being used in the condition are the ones that come from the left-hand side of the join. Or in other words, the columns of the condition are a subset of the columns of the left-hand side table. In the interest of time, I'm going to skip this, but work it out on your own. This is basically this right here is checkpoint 2. This slide, this rule at the bottom right here is almost let's say 80% of what you need to do in checkpoint 2. So work it out on your own, and we'll get back to it when we talk about that. Commutativity and idempotence. So Amneet asks if commutativity and idempotence would work the same way on the right-hand side. Yes, completely. So we're starting. Let's see if I can do. Yeah, you can see the cursor here. So whether we go from here to here to here is pretty much the same thing as if we start on the right hand side and go from here to here to here. And in fact, going from the right-hand side is maybe a little bit safer because we can always pull the projection up above the selection without risk. And when we go push the selection down through, push the projection down through the selection, then we have to confirm to ourselves that all of the columns referenced in the selection appear in. All right, apologies for the interruption there. Small technical difficulty, which should now be resolved. Sorry about that. All right. Let's keep going. Okay, so, all right. Selection and cross product. So you can always take a selection and push it down through the cross product as long as it only references columns that appear in R, in the side that we're pushing it down on. And like I said, here's a really simple rule. I really encourage you to work through this example on your own. It's like 3 steps, but this is going to be the majority of checkpoint 2. And let me quickly ask the stream. I'll move on and point out some good responses as they come up. But what are situations where we would like to actually apply this specific rewrite rule? In particular, when would we want to go from left to right in this expression? Quick pause. All right. Projection also interacts with cross product. We can always take a projection operator and sort of push it down through the cross product. The key thing here is that the projection is always going to, like this will always work, but essentially what we need to do is we need to figure out which attributes come from the left and which attributes come from the right, and then figure out like the 2 new projection operators that show up once we push the projection through the cross product need to have only their respective attributes represented. Again, you can try this. In the interest of time, I'm going to move on, and we'll get back to that later. Okay, so in terms of some of the other operations, selection can always be pushed down through union and intersection. It doesn't matter whether you apply the selection to the output of the union or intersection, or to the individual inputs. Similarly, intersection, just like union, is associative and commutative. Projection can be pushed down through union. Again, it does not matter whether you apply the projection before or after the union. And cross product distributes over union. So just like addition and multiplication, union distributes over, cross product distributes over union. Let's do a really quick example here. Again, in the interest of time, I'm just going to kind of overview this. So usually what happens in a query processing system, yes, Soham, like I mentioned on Piazza yesterday, my slides often contain bugs to make sure that you are staying awake. That is the reason. I will stand by that. You are awake. Good job. Karan asks if you need to remember all of these rules. You do not. So if you are building an entire database engine from scratch, I encourage you to use these slides as a reference. hey, wait a minute, that is what you're doing for this project. So these slides will be a helpful reference to you. On exams, I will, if there are questions about algebraic rewrites, I always include a handy little summary of the rules, and I will probably allow some form of open book on the final exam. So no, I do not uh, there are some cases where memorization is important. This is not one of them. And for the most part in this class, I'm happy to have you use references. Memorizate. I'm more interested in your ability to use the concepts and generalize them than I am in you memorizing them. I'm gonna actually get some slightly colder air in here, maybe keep my computer from overheating again. Okay, so so let's keep moving along. The so what a typical query processing engine is going to do is it's going to start with the SQL text that the user gives it, and it's going to start by creating kind of the simplest, naivest, least interesting query plan, or in other words, the least interesting relational algebra expression or relational algebra tree that it can come up with. And the simplest query that you can get is a select from where. I've got some targets, I've got a couple of tables that I'm joining together, and I've got a where clause. And so what we're going to do is the targets are going to, where did I leave my pen? And so essentially what's going to happen here is we're going to take the targets. They're all going to go into this final projection. We're going to take the where clause. That's going to become a selection that's sitting under the projection. And then we're going to take the tables and we're going to compute a multi-way cross product of those tables. And because it's associative and commutative, because cross product is associative and commutative, the specific order doesn't actually matter. So once we have this tree, now what we want to do is essentially turn it into a more efficient version of the same tree, something that we can evaluate a little more elegantly. So we're going to combine all of these rules together, selection pushdown, selection decomposability. So for example, here, the clause s.d equals t.d, that spans the two sides of the cross product, whereas all of the other clauses r equals b, s.c is less than 5, those only come from the left-hand side. So we're going to decompose the selection, and now that we've decomposed it, the right hand, the lower one can get safely pushed down into the left-hand side of the join. Now, s.d equals t.d, that is an equijoin, and as I kind of hinted at last week, that's something that we can evaluate really, really efficiently. So we're going to convert that into a join operator. Then we're going to go through the same process. We're going to split the two conditions, and s.c is less than 5 only applies to the right-hand side, so we can push that down there. And now we have another really nice join condition, so we can convert that cross product into a join operator. And what we're left with at the very end is a query plan that looks that we can actually evaluate fairly efficiently. There's a couple of other optimizations and transformations that might make this a little bit more efficient. I'll get into those in just a moment, but basically this is the idea. Alex asks if it is faster to decompose the selection into multiple stages, or was this done just to substitute other faster algebra? The latter. In general, you don't want two selection operators, and in fact, usually the rewrite rules are implemented in a way where you just kind of have the selection that you can push down below the current operator and the condition that you just keep there. I'm being pedantic here and going through step by step um, just to stay with the rigorous mathematical um, grounding of this model, but the implementation can be a lot more cleaner. And in general, you're right. There is no need to split the selection into multiple chunks unless you're going to push one of those chunks further down into the query. Hopefully, I've answered that question. Give me a shout if I haven't. Okay, so to recap, what a typical query optimizer will do is it'll just start with a really naive translation of the SQL into a relational algebra expression, and then we'll apply these rewrites to get a version of the query, a relational algebra tree that is more efficient, or at least that maps to a more efficient way of computing the query results. That's still a little bit abstract, so let's go into it a little more deeper. So the first question is, well, I've given you a bunch of rewrite rules, and many of those rules are bidirectional. I can apply them in, go from left to right or right to left. So which of those are actually relevant? Okay, so again, this is a little bit of an info dump, but I'll try and justify them. And if you have questions, please speak up. Selections, we've been talking about this for a couple of lectures now. The earlier you can get rid of data in the query plan, the better. So if you have an opportunity to push a selection down through another operator, whether it's a projection, a join, or a union, you almost always want to do this. For joins, joins are always going to be better than cross products. As we'll talk about in a couple of lectures, a cross product, the only real way to implement a cross product implementing a cross product requires an n squared runtime. And with a join, if you have the right condition, then you can almost always come up with a better join algorithm. That's not always the case, admittedly, but very often you always want to take a selection sitting on top of a cross product and convert it into a join. Projection pushdown is another useful trick because again, it removes data. It doesn't remove rows, and this is kind of one case where it's sort of situational, because when you do a projection, when you do a filter, usually you don't really pay a cost. You're applying the filter, but then the data either completely goes away, the entire record goes away, or it stays. With a projection, because you're removing attributes, that usually turns into a memory copy and sometimes a memory allocation. So pushing projections down, having more projections throughout your query plan is not usually as helpful as having more selections. But there are cases where this is beneficial. For example, if you can push the projection all the way down to the point in the plan where the data is being loaded, like right above the data load operation, you're usually going to be doing a memory copy there anyway. So you can essentially amortize the cost. It'll be a lot more. That is a situation where it's valuable. Okay, so these are the ones we've kind of that are always good. There's also a handful of situational algorithms, situational rewrite rules. So joins are commutative and associative. So the order in which you evaluate the joins can actually have a fairly big impact on the query runtime, because each join essentially is going to create more data, or in some cases, it's actually going to filter out data. The output of the join might be smaller than the input. So picking the right order is also something that query optimizers really have to look at. The order in which joins and unions are evaluated similarly may affect the query runtime. If you do the join below the union versus above the union, you might end up with different query runtime. Manasa asks if there's a case where we're left with a selection and a projection at the end, which one should we do first? Fantastic question. So usually both selection and projection are things that you can implement, that you can tie into what's called the access path. The when you load the data set, it if you know which attributes you're going to need, you may not necessarily need to load all of the attributes. So you have one kind of component of your system. I'll make this a little more precise on next Tuesday, but you'll have kind of one component that is responsible for loading the data. And if this component knows it just needs a subset of the query, a subset of the attributes, fantastic. It only needs to load those attributes. And similarly, if it knows it only needs to load a subset of the rows, again, it can focus on loading those specific rows. This becomes even better if you have an index on that structure. This is a fantastic question. I'm basically going to answer it by saying at the end of the day, what you're going to do is create a new operator, or in your implementation, and this is actually what Spark does as well, is create a new operator that combines all three, the base data, the selection, and the projection into one data load step. Kind of like we have joins are a combination of a selection and a cross product. Merging those two allows us to create a more efficient operator. What Spark and what I will encourage you to do is to create one operator that combines all three. That's a fantastic question. Right, and in particular, that gets me to kind of the last thing, which is access paths. There are certain, if we have the data organized in the right way, then we can make selections on top of that data set, as well as joins with that data set really, really fast under certain circumstances. And we'll get to that in a couple lectures as well. Some of these rewrites you always want to do. There's really no question about it. Other rewrites will need more information about what situation you want to do those in. And that's what we're going to, once we're done with kind of setting up checkpoint one, that's pretty much going to be the rest of the first half of this class. We're going to look at different ways, different algorithms, data structures, and tricks that we can use to make query processing fast if we know the right things about the data. Karan asks, how do we know that the query is in the best optimized form? Fantastic question. I will answer that in a couple of slides. General query, okay, so basically what I'm getting at here, like there's a bunch of these rules that we want to apply. What a typical query optimizer is going to do is process the query in a couple of steps. It's going to first, I mean, there's a handful of these heuristics, like I said, that you always want to do. There's never a situation where they're not beneficial. Those you just apply right off the bat. Wherever you have an opportunity to apply them, you apply the transformation. Now there's a bunch of these that are not as obvious, and what a typical database optimizer is going to do is it's going to start just enumerating a bunch of possible plans. It'll list out, for example, all of the execution orders of the join and union using commutativity, associativity, and distributivity to list out all of the possible join orders. Now, there's going to be a ton of these. If you have, so the number of these orders grows combinatorially in the number of joins and unions, actually exponential in the number of unions. So there may be a very large number of these. So typically what an optimizer will do is kind of pick some subset of them. And there's various tricks for doing this. We'll talk about a little bit later when we talk about optimization. And There's also other kind of optional things that we can look at. Well, what kind of algorithms do we have for each operator? What kind of data structures do we have that we can leverage to answer the query more efficiently? And once it has those, it'll look at all of these plans that it's chosen to look at, and estimate how long each is going to take. Now, this is a really awkward estimate because we don't actually know how big the data is. We may know some statistics about the data, but we don't actually have a full runtime. So what we need to do here is kind of just make an educated guess about how long each is going to run, pick the one with the lowest cost, and that's the one that we actually convert into our final representation and execute. Now, one note here: when building an optimizer, like I said, the cost is going to be an estimate. So while we want to optimize for cost, we also have to acknowledge the fact that the cost is going to not always be precise. So what a typical optimizer will do is not optimize for the best cost, but rather it'll optimize for kind of the best risk reward. So it'll optimize for the best cost while at the same time having the lowest chance of having a horrible cost if we misestimated, if we made a mistake in our estimates. Okay, so how do we do this in Spark? And at the end of this, I promise I will answer your question, Karan. So I want to, but before I get to that, I want to kind of show you, well, I introduced some components of Spark's logical plan and tree node last class. I want to kind of show you how that maps to the rewrite rules that we're talking about here. Now, one of the rules that we said was kind of always a good idea is to take a selection and push it down through the tree. And one example of that is taking a selection and pushing it down through a projection. The same thing is going to hold for the other operators, but this one's just nice and simple. And just in case anyone is concerned, like I said, when we're going in this direction, C is always compatible because we're pushing the selection down through the projection and not the other way around. So I introduced this operator, this function on Spark's logical plans called transform. And just to recap, what happens with transform is we're going to give it a couple of patterns as case clauses, and it's going to just look at the entire tree, and anywhere it sees a particular pattern, anywhere the set of nodes or the subtree of nodes is matched by this particular pattern, um, the transform operator is going to let us plug in a new thing. And well, this is pretty much as literal a translation of the pattern to code as I think you can get, because, well, what do we have here? What do we have here? So we have a selection sitting on top of a projection, sitting on top of some arbitrary child node. And, well, how do we represent selection in Spark? It's a node called filter. And that filter node has a condition. So we're basically looking for filter nodes that have a condition. Well, okay, great. And in particular, we're then looking for filter nodes that have as a child a projection that has some attributes in it. And that projection had also, well, better have some sort of input. We don't actually care about what the input is. We just care that it has to be there. So not so much caring. And well, what happens then? Well, we're going to take the entire thing and we're going to restructure it. So again, there's a very nice one-to-one mapping between the components of the replacement and the components of the pattern that we're matching it against. Questions? I'll give people a moment or so. Right. So the match statement, the case clause, essentially is where you define the pattern that you're looking for, and then the transform is going to let you match instances of this pattern in the tree with the corresponding replacement. Now, this example here is a slight oversimplification. Spark internally uses extended relational algebra. This is extended projection, not the simplified projection that we've been talking about so far. But hopefully this gives you some sense of how this works. Yeah, okay. So if I apply this particular rewrite to this tree here, a filter sitting on top of a project, sitting on top of another project, sitting on top of an arbitrary child, what's going to happen? So if I call transform, what am I going to get as an output? There's 53 of you watching right now. So let's start with the pattern. What pattern am I looking for, and does it occur in this expression? And if so, where? Did I lose everyone? Oh, okay, great. So project. Okay, fantastic. Good job, Jane. Right. So what we're gonna see here, is this part of the tree is matched. That's the pattern that we're looking for. Or equivalently, this part of the tree is going to get matched, and this is going to just be the child. So we're going to take this entire thing, the transform is going to, if we apply one, let's say one step of transformation, what we'll end up with is pi a1 sigma of c and pi of a2. So that's one rewrite. Now what? Okay, Sunny notes that kind of if we apply the rewrite, maybe what'll happen is instead we want to essentially if we keep applying the transformation rule, we'll end up with something that looks like the projection of selection of R. And ultimately, that's what we want to get. Um, Ultimately, that's what we want to get. But the order in which this happens is actually important. So what do I mean? What do I mean by that? Right. What do I mean by that? So answering your original question, Karan, I'm going to essentially what you want to keep doing, you want to keep looking for transform opportunities and keep just searching for opportunities to rewrite the query. And then when you get an opportunity to rewrite it, then you essentially want to apply that transformation and just keep doing that as long as there are opportunities. And the naive way to do this, and what many optimizers kind of, if you peel away all of the optimizations, what essentially they are doing at the end of the day, it looks a lot like this, where you have a plan and you just keep applying the transform, and you just keep applying it until the thing that the transform gives you back is the same as the original expression. In other words, you just keep applying the transformations until there are no more opportunities to apply the transform. Um, so, Karan, hopefully I've now answered your question, at least with a naive solution. There's a slightly more intelligent way of going about this in some cases. So in particular, selection pushdown, we're always going to be taking a selection operator, pushing it down within another operator. So the new opportunities for applying selection pushdown are always going to be below the original rewrite. Oh, sorry. Meant to say mention this naive approach is often referred to as a fixed point computation. Essentially, we're applying the operator until we reach a fixed point where every time we apply the operator again, it just always returns the same thing. It's fixed. Right, sorry. So like I was saying, every time we push a selection down, we're potentially creating a new opportunity to push the selection down through its new child. So what Spark gives us is a couple of rewrites that allow us to control the order in which the rule is applied. Transform up is going to start from the leaves, look for opportunities to apply the rules at the leaves, then go up, then go up, then go up. Whereas transform down is going to start at the root and keep looking for opportunities to apply going down. So in this particular case, we are essentially looking for, because we're always going to be creating new opportunities for transforming below the current node, transform down is actually going to allow us to fully push the filter down to the bottom of the tree, or at least as far as it'll go, in a single pass, whereas transform up would require us to do multiple passes. Essentially, each time we'd take one, we'd push things down once. If you just say transform, you're essentially leaving it up to Spark to decide which of those two you want it to do. Right, so you can do the same thing with other operators. In the interest of time, I'm not going to go to depth too much, but the basic idea is essentially the same. You to implement a selection pushdown through union, you would do literally the same thing. You'd pattern match for filter operations that are sitting on top of a union, and then you'd create a new union of the filter applied to each of the individual children. Union has a couple of other parameters that we're going to ignore here. Okay, so this is basically it. We'll go into a lot more depth into how to interact with Spark's logical plan and Spark's expression classes on Tuesday. And then when we start talking about checkpoint 2, we'll go into a lot more depth on how to use pattern matching to do query processing rewrites. But I kind of want to give you at least a little bit of an intro to the idea here. So with that, any final questions? I'll be, if there are final questions, I'll be hanging around for a little while. Otherwise, I will see everyone on Tuesday. Please remember, checkpoint 0. If you haven't already done it, it should literally be either 5 minutes or it should literally be like five to 30 minutes of your time. And if you haven't done it already, just get it out of the way. It's literally 5 free points. Harsh, how to predict such Plato when converting? I do not understand that question. Let me answer Karan's question while you respond. So Karan asks what to expect for checkpoint 1. So for checkpoint 1, basically what I'm going to be asking you to do is implement very basic SQL query processing. This ends up being on the order of 200 to 300 lines of Scala code. It can be done in 200 to 300 lines of Scala code. Essentially select from where the from clause can have a join. We're not really going to. Oh, thank you, Darshana. Great. So there's, I think we're down to about 53 students. So there are 7 of you who have not completed your submit. Oh, sorry, 8, since 8 or 9, depending on whether I have a submission. Um, so yes, the 7 or 8 of you who have not yet done checkpoint, even tried to complete checkpoint 0, please do that. I don't want to be up all night on Monday answering questions from you getting stuck setting things up. Oh, thank you, Darshana. Okay, so continuing my answer to Karan. So what do you expect for checkpoint 1? Essentially, what I will give you is a simplified chunk of Spark that contains logical plan, contains expression and all of their respective uh, instantiations. I will also give you Spark's parser. So essentially, I will be asking you to write code that reads in a SQL statement or a series of SQL and create table statements, and that produces answers to those on data that I provide. The You will get code that if you give it a SQL expression, you will get back a logical plan. That is 2 lines of Scala, and I will give you those 2 lines of Scala. The interesting thing is basically going to be starting from the logical plan, how do you convert that into something, into actually an answer? And we'll go over some of the details of that on Tuesday. So Harsh asks, how do you know where to stop when converting so it won't end up going back to the previous point? And that's actually a really good question. If you have some sort of rewrite rule that goes back and forth, that kind of keeps changing things, you need to be a little more careful there. I am going to tell you right now that in order to get an A, you don't even need to do a fixed point computation. You take For an A in this class, or at least for project 1, all you will need to do, sorry, for project 1, no optimization will be required. You're welcome to do it, and there will be kind of a couple of not bonus points, but there will be a leaderboard. So if you want to kind of bump yourself up the leaderboard and get a head start on checkpoint 2, fantastic. But you will be able to get an A without doing any optimization at all. For checkpoint 2, that's where the optimization kicks in. I will tell you right now that you don't actually need to get a fixed point. As long as you're intelligent about whether to use transform up or transform down, then the always good rewrite rules, selection push down, join conversion, all of that stuff, you can do that without you can do that in a single pass of transform up or transform down. Um, That being said, what usually happens in a typical optimizer is, well, it'll look at the either the last one or the last n plant or trees that were generated, and if any of those trees are the same as the current one, it's going to stop. There's usually kind of an upper bound on the number of iterations it will do as well. So if it gets to the end of that, um, it'll just assume that there is some sort of repetition going on. Um, but yeah, it'll keep looking for optimization opportunities until it gets to the very end, until it either runs out of iterations, hits some sort of threshold, uh, hand-selected threshold, or just kind of looks until it stops changing, or until it reaches kind of a steady state. Suki asks, is checkpoint one connected with the remaining checkpoints? Yes. So checkpoint one is essentially going to be a getting off the ground kind of checkpoint. Once you're not going to be asked to answer queries efficiently, at least not super efficiently. Um, the results that we're going to be working with relatively small data sets and relatively simple joins. Checkpoint two, you're basically going to take checkpoint one and add optimization rules, add some slightly more interesting algorithms. Checkpoint two is probably going to be the linchpin. Once you have checkpoint two, three and four kind of branch off into slightly different directions. But checkpoint one is kind of your foundation. Checkpoint two is like the first floor of the house, and then checkpoints three and four, those kind of just build on top of that. Thank you, Darshana. Yes, shout out to Darshana. Go to her office hours. Go to my office hours as well. But like she is waist deep in Scala code right now and in Spark code right now. So like she understands all of this in intimate detail. So answer like she will be able to answer all of your questions. And yeah, my office hours are there too. I encourage you to come to those as well. For the next checkpoint, we'll be cloning the modified Spark SQL or some. So I will be sharing a jar file as well as the associated Scala doc for the relevant part of excuse me, for the relevant parts of Scala of Spark. Excuse me. Um, so you won't need to clone anything. You'll basically just take the repository that you have right now, and I'll by Monday there will be a published library. You can bring it in through Maven. You will be able to bring it in through Maven. Um, all of that infrastructure will be there. Hopefully, I've answered your question, Hari. Um, Let me know if you need some extra clarification. Great. All right. Sounds like uh, I've caught up with the question queue here. So if folks have more questions, I'll be on Piazza for the rest of the day. Give a shout there, or I will be around on Monday for office hours. Failing that, see y'all on Tuesday.